Good afternoon, everyone. I'm Priya Natarajan, an astrophysicist and faculty in the departments of astronomy and physics at Yale. I also serve as the current director of the Franke Program in Science and the Humanities, the flagship interdisciplinary program at Yale that catalyzes intellectual exchange and collaboration across academic disciplines. I am delighted to invite you all to the monthly convening of our Nature of Inference Colloquium series. First, I would like to start by recognizing the generosity of Mr. and Mrs. Richard and Barbara Franke, whose support of this program and many others at Yale have vastly enriched intellectual engagement and innovative scholarship. Then I would like to remind you all that as we are recording this event, that all participant videos and microphones will remain muted. Please go ahead and submit any questions you might have through the Q&A feature. Dr. Ty Camp and I will be managing the Q&A at the end of today's talk. So I am delighted to welcome today's speaker, partly because he's one of our own, distinguished member of our own faculty, Dr. Nisheeth Vishnoi. And before I tell you more about his various honors, accomplishments, and so on, I have to add that one of the particular pleasures of having one's own colleague speak is when you have someone like Nisheeth who is so incredibly intellectually curious that it is going to be an utter treat, I promise you all, to hear him speak today. So as you all know, in this wonderful series, we've been exploring how we know what we know in terms of generating new knowledge in a range of disciplines that study varied phenomena, be it protein folding and structure and its implications and impact on how our body functions, or how we build models of complex physical systems like climate and make predictions. Today's speaker, Dr. Nisheeth Vishnoi, is going to talk to us about perhaps one of the most complex systems that we encounter, how we individually and collectively make sense of the world, the ways in which we model the world in order to do so, and the limits of, therefore, what we know, delving more deeply into the profound questions of where many of these limits of what we can know and what we do know arise from. It is a real pleasure to have one of our own faculty members, a distinguished member of our faculty, Dr. Vishnoi, talk to us today about bias in algorithms. So to give you a sense of the breadth of interests and the range of wonderful original scholarship that Nisheeth has been engaging in, let me tell you a little bit more about him. So he is the Bartlett Giamatti Professor of Computer Science and a co-founder of the Computation and Society Initiative at Yale. He studies the foundation of computation, and his research spans multiple areas in theoretical computer science, optimization, and machine learning. He's also interested in understanding the nature and society from a computational point of view. His current focus includes studying entropy. The range is going to be astounding, the emergence of intelligence behavior, and ethical problems at the interface of artificial intelligence and society. He has many, many honors, and I have cherry-picked a few so that I don't keep you from listening to him for much longer. He was the recipient of the Best Paper Award at the IEEE Symposium on Foundations of Computer Science in 2005, the IBM Research Pat Goldberg Memorial Award in 2006, the Indian National Science Academy Young Scientists Award in 2011, and the IIT Bombay Young Alumni Achievers Award in 2016. And, multiple Best Paper Awards at various conferences. The one that is relevant to our talk today is at the ACM Conference on Fairness, Accountability, and Transparency in 2019. He was named an ACM Fellow in 2019, and his most recent book, Algorithms for Convex Optimization, was published by Cambridge University Press. And as is customary with this colloquium series, it'll be followed with a conversation with another distinguished practitioner who brings a slightly different perspective. So following Professor Vishnoi's talk today, we will have the conversation on Monday with Professor Alexander Madry, who will lead the post-talk discussion Monday evening. So without further ado, let me turn the floor over to Nisheeth. Nisheeth, we are delighted you are here and are really looking forward to hearing you.
Thank you, Priya, for that very generous introduction. And thank you all for being here. Good afternoon, good evening, wherever you might be. So if it's okay, I'm going to share my screen, Priya.
Yeah, please go ahead.
So the topic of the talk today is bias in algorithms. And my plan is to give the listeners a sense of how, in this very objective world of algorithms, which live in this very precise mathematical framework, uh, human-like qualities like bias can emerge. And what can we do to intervene and mitigate these algorithmic biases? And in the process of trying to figure out the ways in which we can mitigate these biases in the world of algorithms, we will also see at the end how we can gain some insight about mitigating bias in the world of humans itself. So let me start by setting up the framework in which the world in which we live in. So it's not news to anybody here that humans live in an algorithmic world. Let me make this a little bit more precise. Humans, us as a society, are consuming a huge amount of information through various online channels. Unlike the old world, a few years ago, where we were looking at newspapers and so on. Now everybody gets their news through Twitter, Facebook, or equivalent. We connect with people through these social applications, which are made possible through this World Wide Web or internet. We are also increasingly using algorithms in the context of governance, policy, and so on. And last but not the least, many of the utilities that we consume today, from ride-sharing apps to online shopping platforms, are all governed by decision-making algorithms, which are constantly learning about human preferences through the data that they generate and presenting information often in a personalized manner to these individuals. And this information is affecting who we are as individuals and giving shape to the society in a very different way and at a very different scale than we imagined previously. So this is the context that I'm going to be talking about. And let me say a few words about algorithms. And I'm going to focus on artificial algorithms, which largely developed, the formal study of algorithms in the discipline of computer science is about, I would say, a bit less than 100 years old, starting with the works of Turing and others, who started looking at algorithms or formalizing the notion of algorithm. And in the last few decades, we have come a very long way in designing artificial algorithms, which have shown the ability to mimic some of the most complex natural algorithms. For instance, Priya had mentioned protein folding. I mean, one of the most recent successes of artificial algorithms is the ability to predict the tertiary structure of proteins, which has been one of the main challenges in this whole. Not to mention beating the best players in the most complex games, predicting weather, and I guess the more relevant algorithms that we are going to talk about a little bit today are things like, algorithms used in courts and by judges, which decide who goes, who gets bail and who doesn't get bail, or artificial algorithms, which are deciding who gets loan and who doesn't get loan and so on. So there is a vast and complex landscape of algorithms. Very, very roughly, you can think about an artificial algorithm as, in today's world, as something which has a few components. not necessarily all of them, but there may be some data available from which the algorithm might want to learn. To learn something, we need to have a model. We need to figure out, what is allowed for us to learn. I mean, when we're trying to learn from data, what are we allowed to use in that learning process? And that's the step that I'm calling the statistical or reasoning model. And finally, once you have decided on the model and you have the data, you will need an algorithm which can then find the best model from this data. And we can talk a little bit more about in detail. So this is just a very high level view for you to get a sense of what many of these algorithms look like. And the point that I would like to highlight is that these decisions that we see here, right from data to selection of model, to selection of training algorithm, to selection of anything involves humans. And so this is why we call it, I mean, artificially intelligent algorithms, because humans are making these decisions. One thing that remains common, no matter which artificial algorithm you look at, is that they live in a very precise world, which is governed by unambiguous mathematical rules. And somehow people and society associates objectivity to mathematics, and we can go into that at some other point. But there is some association of objectivity to the mathematical precision, and so there was some expectation from these algorithms that they should also be objective and not show human-like qualities. Unfortunately, this is not true, and I guess this is not news to anybody here. Nevertheless, I will still go through some examples. I would say about less than a decade ago, many researchers started auditing algorithms which are being used in very, very broad settings. For instance, search. So you go on something like Google and search for Google images and search for something like a CEO. And it's not like Google just has these 15 images of CEO. It has billions of images probably which are tagged CEO. And then based on what it understands of you and the word CEO, it'll pull out a small subset of images for you to see. And this process of, why small? Because your screen is small, your attention is small, so you can't really process billion images. And perhaps that's not what you're looking for. So this process requires solving an algorithmic problem of selecting a subset for a particular individual to view. And presumably there are some objectives. Why is, the search is for free. So there is clearly some objective of showing these images to you. And one reasonable objective that many of these companies have is to maximize engagement. So we keep giving you good results so that you keep spending time on our platform, so that we can keep showing you ads, and so that you can go buy products, right? So more strikingly, and I guess less strikingly and more strikingly at the same time, some very so facial recognition has been very important in this whole fight against algorithmic bias. And their interesting and important work of Joy Bulwomi and Timnit Gebru showed that off-the-shelf classifiers manufactured by some of the most standard and well-trusted companies such as IBM showed remarkable differences in the ability to classify people based on their protected attributes such as race and gender. And since I talked about showing advertisements, showing advertisement is one of the core business of many of these platforms. And there were biases. It's not surprising, but it was observed that women get shown ads for low-paying jobs while men get shown more ads for high-paying jobs. So, okay, so as somebody who might have not seen this before, or who's skeptic, say, okay, this is what is being shown. What is the problem with this? Anybody can show whatever they want to you. So what is the issue? The issue is that the output of these same algorithms can alter human perceptions. Okay, so it's not like just seeing has no impact on us. Seeing is believing in this case. And the same studies which found these biases also found that people who may or may not have an opinion about gender bias or gender and CEOs, after being shown images which are distorted or representations which are distorted, have distorted perceptions of what it means to be a CEO. And I guess we have all gone through this phase in no matter which country you live in, where we are seeing increasing distortion or increasing divergence. Without saying what is right, what is wrong, our worldviews are diverging or polarizing. So polarization has had a disruptive effect on democracy. It has given people the ability to manipulate elections and so on. So there is a lot of stuff to read about here. And these are the core issues that I'm going to address in this talk. But even before I go there, I want to first address the question of anatomy. How does bias emerge? And to understand that, we have to understand a little bit in more detail what I showed in my first slide. How do we learn? What is this? What is going on in these algorithms? So this is not a mathematical talk. So unfortunately, I will not be able to show you a lot of equations. In other venues, I would. But hopefully, I'll give you some concrete idea, more concrete than the first slide, so that you go back with a very graphic sense of how these algorithms operate. So the starting point is the real world, right? So this is the world in which we live in. And when we talk about data, data doesn't live in the real world. Data is collected from the real world. And to collect data, you first need to figure out how to represent data. So I'm a person. If some organization, let's say the US government, wants to collect data from me, they will specify that you need your first name, last name, age, this, social, whatever. They'll give me a template and I need to fill out. In most situations, I really do not have an option. So I need to fill out all this data and give it to them. So two points here. One is representation, which is that I in most cases, I would be given some kind of a form. It could be electronic, it could be a physical form where I fill out information. It could be somebody taking pictures, right? So I need to add a picture, which is also very specifically specified in certain cases. And then certain individuals are selected for such data collection. So if you are doing, let's say, a survey or trying to estimate something about a population, it's infeasible to collect data from everybody. So you will select some subsample. Now, to what extent the subsample is good is often not clear. So data has these two major components. There are other bells and whistles, but in the first order understanding of things, this is what it is. Now that you have a collection of data, you want to learn from this data. And learning happens in a hypothesis class. So the more complex the hypothesis class, the more you have the ability to learn. And most learning algorithms will fix a hypothesis class. And these then determine, these hypotheses are parameterized. So and not, I mean, it will not be the case that one hypothesis will explain the data. So there may be many, many hypotheses which explain the data. So then comes the question of which one to choose. So which is the best hypothesis that will explain the data? So we have to fix a mathematical notion of accuracy or something, which helps us select from this wide class of hypotheses, the one which is the best. Once we have made these choices, we go on to find the most accurate model and using something called the training algorithm. And that gives rise to the decision-making algorithm, which then is used in the real world. So maybe this algorithm will be used to decide who to give loan or who not to give loan. And that has a direct social impact. Whoever gets loan, their life changes, and whoever doesn't get loan, their life probably worsens. I mean, given the fact that they're looking for loan. So this creates this feedback loop. I mean, these output of these algorithms could also feed into other algorithms and so on and so forth. So the design choices are human choices. They are driven by human motivation. So each step of this process, there are humans who are deciding, and their decisions are motivated by what they think is valuable. So the real question is, who decides? Who does this benefit? And who is harmed? And all of these questions are very important. I mean, and these questions are generally not asked in the design of algorithms, because whoever is designing the algorithm, it's their benefits that certainly are incorporated. Very, very rarely there's a discussion on who could be potentially harmed and what can we do to mitigate those harms. So in all of this, algorithms end up being brittle and gain the ability to encode human biases. So at this point, I guess it should be. I mean, the point that I want to make is that, well, one more point I want to make is that, one of the reasons why this study on algorithmic bias got really caught the attention of media. I mean, that's really where it got into, is because in the end, what does it show? It shows, and it gives definitive proof that humans are biased. If I catch somebody and say, hey, you're biased, they may argue and wriggle out their way through that discussion, and in the end, nothing conclusive came out. But if the same person hands me an algorithm which I can keep repeating again and again, I mean, keep running it again and again without any further intervention, once the algorithm is there, that's it. And then you can say, look, I mean, if you are not biased, then how can this algorithm be biased? So it gives us a definitive proof. Now, without pointing fingers, it gives us a definitive proof that humans are extremely biased. And that's what these algorithms are picking up. So it gave us a lens into our own existence. And it should not be surprising that while studying, or as the bigger goal of studying algorithmic bias is to try to understand various ways in which humans can be biased and design frameworks and policies to mitigate those biases. And I'll come to that towards the end of the talk. So just a little bit more graphic image of what goes on. If I take a simple example, let's say, of who to give loan or not, let's say the society consists of, this is a very toy caricaturization of the problem. This is not how it works, but it'll give you a mathematical sense of what goes on. So there are people, some people, let's say, are women, and some people are men. I understand that things are not binary, but for this thing, let's just consider that. And traditionally, there has been disparity because of the construction of various social and political systems. Men and women in our society are not equal, unfortunately. And suppose we choose features corresponding to women. So suppose I pick two features. Features meaning what about the individual do I need to decide whether to give someone a loan or not. So let's say as a bank manager, I decide I'm going to ask to encode to the extent to which the person is educated and the income. So let's say these are the two coordinates here that you see, two numbers associated to each person. Some mathematical encoding of their highest educational degree, in this case it's 5, and some mathematical encoding of in this case it's 10. This could be 10,000, this could be 10 million. But yeah, without going assigning units to it, let's just think of them abstractly. And then many of these algorithms also need some kind of historic data. So in the historic data, I would probably also need to know whether this kind of a person ended up repaying their loan or not. This information is useful for me, but I don't want to give loan to people who are not going to pay back to me. And then, when I talked a lot about models, so models could be as simple as selecting lines, straight lines, to divide the data into positive and negative examples. So plus means positive examples and minus means negative examples. So I'm looking for a rule which will, or it could be something more, it could be something very complicated. For example, you could choose very complex curves in high dimensions, which can kind of cherry pick the points if you like. So this is the traditional machine learning algorithm, and this is what, these kinds of images are more associated to deep learning algorithms, where there are many parameters, very high degree polynomials, and they can really learn arbitrary concepts. So then the nice thing about those learning models is that they are universal, in the sense that they can learn any function. So in all of these choices, and this is just a subset of the choices, there can be issues. We already talked about societal historic biases. What may happen? You may say, oh, I'm not using gender of a person, so what's the problem? These numbers are fair. No, these numbers may not be fair because, as I said, traditionally women might have lesser education, lesser income. So these numbers might be tilted against them, right? And same about this, right? The labels and other, there can be inaccuracies, there can be misrepresentations in your data set. You might have more men than women, so you don't learn much about women, and so on. And models, of course, can further exacerbate bias in a very mathematical sense that I'm going to omit. But all of these things can very concretely lead to issues. But you can see that, these choices that we are making these choices as humans. Yes, in the end, we design an algorithm, which is a precise object, but these are the choices we are making. Let me give you another example of bias, which is something other than gender or race, which we talk a lot about. Something which I mentioned earlier in terms of polarization. And this is bias in a different space. It's in the space of opinions, okay? So imagine that this is you, and this is your Twitter or Facebook feed. So, let's say you log in now, and between the last time you log in and now, many of the people who you follow or are your friends would have generated posts, okay? So this is the set of all posts that Facebook or Twitter can potentially show to you. And this is their key thing. This is their billion-dollar algorithm, the content selection algorithm, which from this huge set for each individual creates a personalized feed. And I have chosen to represent, again, as a toy example, where the set of all documents or set of all news articles or set of all tweets are divided into two types, the red type and the blue type. Okay, the situation on the ground is more complex, of course, but let's say this is the case. And this content selection algorithm also gives you a very limited ability to interact with your personalized feed. So you can say, I like it or I don't like it. For a very long time, this is what it was. And now you can do perhaps a little bit more. So this information, the reason why this information was so simple, was kept so simple, is because then the signal reaching the content selection algorithm was very clear. And so it could use this to show you the next personalized next time when you come, to show you a personalized feed again. So what is really happening? So what is really happening in this content selection algorithm is that for each individual user, it represents each individual user as a point in some very high dimensional space of opinions or articles. So there is this very high dimensional space consisting of all possible articles classified into red and blue. And in the beginning, the algorithm has no opinion of you, no prior of you. So you start off somewhere in the middle. So when you start off, your feed will look kind of balanced. But then you click on something. So when you click on something, the algorithm thinks, okay, this person seems to like this post and the post is red. So let me change its representation a little bit towards red. So, and this is a very precise movement that happens in the space. I mean, these dynamics are governed by the the profit function. So what is the goal ultimately? The goal is that the content selection algorithm should show you feeds which you will keep which you will keep clicking on, right? And so that you don't go away. So they do that. So maybe now a new feed is generated, and maybe now you click on a blue one. And so now you move a little bit to the blue and so on. So over a period of time, in a relatively short period of time, what happens is that, and what we see happening is that two people starting from very close to in the center can diverge, their opinions can diverge. And what that really means is that you kind of, from the algorithm's point of view, you move into the deep blue or deep red space. And after that, your feeds are basically going to be just mostly blue or mostly red. I mean, take all of this with a pinch of salt, okay? So this is caricaturization of what is really happening, but it's pretty close to what is happening. So what can we do? These kinds of biases are emerging. So what can we do? So we can focus on correcting data. We can talk about participatory design of models. So we have to take into account not only Facebook or Twitter's preferences or Google's preferences, but also preferences of the individuals, which has not been happening so far. We can, once we agree on the joint goals or the joint models, we can try to design algorithms that are now constrained to be fair in some sense. And just like we have a police and a legal system and a police system which keeps auditing and doing things to control people, we have these algorithm audit units or companies or whatever, mostly civil civic bodies which are studying the impact of algorithms on users. So here, there's a little problem though, that when I talk about fairness or bias, it's not just one thing, okay? It's many things possibly, right? So when I say something is not fair, it's not clear what it means. It may be clear to an individual who has experiencing fairness, but when we talk about designing algorithms, we need to be precise. What do we mean? And what that really means is writing down a precise metric, a precise way to measure unfairness or bias. And this picture, which is still partial, kind of probably gives you a sense that things are very complex. The landscape of fairness is very complex. There are many, many different types of notions of fairness that you can consider. There are at least 40 which have legal backing in various contexts. And in each context, there are multiple stakeholders. And you can prove theorems which say that you cannot design algorithms which satisfy multiple notions of fairness. So unfortunately, you will have to fix the context, and in that context, stick to a definition or notion of fairness, and then say, okay, let's design algorithms in that framework which are fair. So this is where some of my work, which I've been doing over the last few years, comes in. And one of my main contributions is to specify a very general framework for users to encode their fairness constraints. So we saw that the landscape of fairness constraints can be very complex. And what we did was to kind of figure out what's the simplest possible way for us to mathematically encode these fairness constraints, and then design algorithms which are constrained to be fair. When you add constraints to a system, so this is an algorithm here, which is computing some function from data. The moment you constrain it, a natural question arises is that the previous algorithm is not going to work. So who will design this new algorithm, and whether it's even possible to design an efficient algorithm? So, so efficiency is the keyword here, because you can imagine having you can write down a function which you would like to compute, but then if it's not efficiently computable, it's not going to happen, in the sense that, the size of data and the size scale at which we are operating is so huge that the problem should also come with some efficient algorithms. Otherwise, you will have to pay some computational price of fairness. On the other hand, from the point of view of, let's say, a company like Twitter, and if you say constrain Twitter's feed, right? So you give some controls to the user and say the user will control to the extent the content that they want to see. Then Twitter will object immediately and say, but now we don't know what the engagement metrics will be, and that can really wipe us out from this market. So we're not going to agree to it. So this is what you may think of as price of fairness. Fairness is a great goal, but in this capitalistic society, who pays the price of fairness? Who will pay the price of fairness? So these are very non-trivial and important questions. And my work has addressed the whole pipeline, starting from identifying bias to fixing data, figuring out the right models, developing fair algorithms, and studying impact. And so not all algorithms, okay, so maybe I skipped a slide. Not all algorithms are equal. Some algorithms are very high stakes. And some algorithm, for example, the algorithm used to schedule the fleet of Hertz car rental perhaps has less impact on at a scale than something like what you see in Twitter or Facebook, or something that you see in Google search, or classification algorithms, or or other stuff. So I've worked on some of the high stakes applications and come up with interesting solutions. You can see more about them. Many of these solutions actually come with new demos. Once we design the algorithm, we code it up, we create a demo for you to see. And you can, if you're really curious, you can go to this website and play around with it. So just to wrap back and say, okay, so what does the picture look like in this world of personalization? Conceptually, it looks like the following: that our framework constrains the algorithm to not let people go beyond a certain point. In retrospect, this seems very simple, but the hard part is in designing new algorithms which respect these constraints. So that's the main contribution of this work. So all of this was assuming that we know data, we know that the data is accurate. And one of the key questions, once you start looking deeper into the system, one of the key questions or key issues that we see is that this data may not be accurate. So besides historical and societal biases, there may be other factors which actually come into the way of data. So let me now explain that. And now we are going towards understanding bias in human decision making from algorithmic decision making. So we'll make a transition, and then I think in next 10 to 15 minutes, I should be able to wrap up. 12 minutes. So Priya, are we taking the questions at the end or in the middle?
If you are open to,
I think this is a good point to pause for a minute and see if anybody has questions about the previous part. I'm open, yes.
Okay. I haven't seen anything appear in the Q&A yet, but we can encourage them.
Okay.
The only note that I have is that, Christina's pointed out, I mean, there are lots of people who are interested, actually would like to have the links posted.
Okay.
Yeah. So.
Okay. So I'll keep on going and think about questions and feel free to interrupt or ask anytime. I mean, I think it's important to hear.
Actually, if I may, I wanted to ask sort of a quick question. So, it's really sort of remarkably clear exposition, Nisheeth, of how our sort of inference systems are biased and how in turn these results that are recovered from these and the claims, whatever, can change us, right? So there's the sort of the power of the algorithms that while they encode our bias, they may also hold the key to mitigating bias, right? So they're very sort of, they are sort of, epistemically, they serve as sort of exposers, right? They're very effective exposers of human bias. So one thing I was curious was, when you talked about assigning scores, for example, we were looking at it, right? So how much of the bias really comes from the fact that, mathematical scores, et cetera, have an implicit ordering, right? Like 5 is better than 10 or whatever.
Yes.
So what if we replace at the top layer, I don't know, I had this sort of a lame suggestion, why not just have colors or something, something that you can at a lower, at a deeper layer map into numbers.
Yeah.
Obviously you have to eventually.
That's a great question. So yes, I mean, I think that's a very good question. And the answer to this is not entirely obvious because as I already hinted that, you can design some beautiful systems which are supposed to do what they're supposed to do. But in the end, you will also need an algorithm to find the parameters of the model.
Yeah.
So much of this stuff is constrained by that aspect of things.
Yeah.
So the reason to go into this continuous space of ordered numbers, simplify everything, the real numbers, not even discrete. I mean, in the world of discrete numbers, there is still more you can do than in the world of continuous numbers.
Right.
So the thing is that these algorithms which optimize are essentially algorithms which work in continuous spaces. Things like gradient descent, gradient flows. I mean, these are inspired again from physics in some sense, and yeah, I mean, this is the set we are working with. So if you face a problem today and you are, let's say, you are an engineer who's working in a company and whose manager gives a task to design something, you're not in the position to reinvent an algorithm.
Right.
So you will just use off-the-shelf algorithm and you will just encode what, you'll just do the minimum thing. You say, okay, let's just encode everything as a real number and ordered in some sense, without putting so much thought into what impact your decisions have on the lives of others. And this also has to do with a complete failure of the education system in some sense, right? I mean, I must say that I take responsibility because, we teach people design of algorithms, data structures, and so on. But a decade ago, nobody in their lecture would even mention the potential possibility of the impact that the choices will have. And now I teach a course in which I make people at least be more aware of the assumptions and their potential impacts.
Right.
We still do the same thing, but we just make them more aware of the impact.
So I see.
And I guess,
yeah. So you're saying that the categories of just changing around the categories of representation is not enough. Because there are too many algorithms lying around, people will just use them. You have to completely start with a new set of categories. But I guess the ultimate limit, as you said, is that we have a well-defined mathematical space in which we live.
Right.
So,
I mean, but it's also a very challenging question. I mean, how do you capture a human? I mean, in what, I mean, all said and done, I mean, if you want to implement this on some kind of computer, then going back to Turing's work, I mean, Turing proved that this is, any computer is equivalent to the Turing machine, right? So at some level, you will have to encode something as complex as human in, let's say, a binary form, or some using some representation, right? So that still remains the yeah, I mean, there is a lot so there is a lot to say here and a lot to do here.
yeah.
So by no means I'm pretending that we have solved any problem. In fact, in this part of my talk, I'm going to tell you how we did not solve that problem that we aim to solve, actually. And the reason, if I may continue, Priya,
Yeah, please go ahead. Yeah.
is that so far I assumed that data, so all of these algorithms that we design work as long as the data is accurate. So forget the issue that women might have historically lower salary than men, but we do assume that the salary is what it is being reported. I mean, that the person is reporting the right salary, right? Or we are measuring information correctly. But as we delve more into human generated data, it becomes even more clear that the data that we record is, first of all, not necessarily close to the data that we should record. Even if we want to record somebody's ethnicity, right? It's not clear that when we look at it, when we record it, we do have that person's ethnicity. I mean, it's like, as a physicist, you can understand this probably. You can look. I mean, you wish you had the true data, but data traveling over billions of years, coming from very far, will add some noise, and all kinds of things might happen to that. So in this context, what we have been seeing is, due to a variety of reasons. For instance, often we need ethnic information, but we don't have ethnic information because it may be illegal to have ethnic information to record. So what do? We impute ethnic information from other things. So that gives rise to a noisy estimate of somebody's ethnic information. Okay, maybe because of privacy concerns, you might have to add noise to data. And what I want to focus on in this rest of the talk, in rest of the 10 minutes, is implicit biases. So much of this data also comes from applying certain evaluation processes on individuals. So for instance, SAT scores. I mean, we here at Yale are in the business of taking decisions about students, faculty, everybody all the time. We get, we want to recruit individuals for some vaguely specified goals. But we choose metrics, let's say SAT score, this, that, and the other. So there is a whole evaluation process. And these evaluation processes can have implicit biases. And the punchline is that much of the stuff that I talked about, this first generation study of algorithmic bias, actually does not seem to work well when data is perturbed. And Alexander Madry, who is an expert in designing algorithms for perturbed data, hopefully will tell you more about this on Monday. So let me just talk about one type of perturbation, which is implicit biases.
Yeah.
And this was the punchline. It can cause, even if your intention was to correct for fairness, if it failed to take into account the precise way in which the data can be perturbed, the effects could be worse than so the intervention could be, the cure can be worse than the cause. Is that the right saying? I think so. No, the effect could be the worse than cure, or something like that. Yeah. Sorry, I'm getting a bit tired. So implicit bias is rampant in the real world. There is lots of evidence. I'm not qualified to do these experiments, but there are very prominent, economists and sociologists who do this. And in almost all aspects of our social interactions, we see rampant implicit bias. To just give a example which is relevant to us, I think there were these studies done where emails were sent to Ivy League professors. The content of the email was exactly the same, except in some emails the name was changed from a male to a female, to a white sounding name to a black sounding name, and there were significant differences in the percentages of responses. Now, one can always argue and try to explain each individual data point, but when there are so many people who study this and find systematic issues, one cannot deny that there is something called implicit bias in this world, which is really the unconscious attribution of qualities or lack thereof of members of particular groups. So the bottom line is that what you observe, the data that you observe may not be accurate. So let's look at a very simple problem, which now starts moving from a problem which you may not associate necessarily to computer science, but nevertheless is still an algorithmic problem. And many of us here might have actually tried to solve this problem. So the problem is very simple. Again, it's a toy problem. Don't take any of this stuff too seriously. The goal is to explain the point. So suppose you have m individuals, let's say 100 individuals. In this case, 1, 2, 3, 4, 5, 6, 7, 8 individuals. And each individual has some latent utility. So this is the true utility of an individual, whatever it is. And I have 4 interview spots. Okay, so I have maybe 1 faculty spot in my department, but I want to shortlist 4 people to interview. So what shall I do? As Priya said, one of the reasons why we are encoding them as numbers is so that we can compare. So the higher the number, the better it is. So our goal is to shortlist these 4 people or n people, which maximize the cumulative latent utility. So this is a very simple algorithm, actually, which I think everybody here, you don't need to take an algorithms class to design such an algorithm, which is to first find the one with the maximum, remove them from the set, find the next one, remove them from the set, find the third one, remove them from the set, find the 4th one. That's your set of 4 people that you would like to interview. Okay, this is very simple. Even a child can solve this problem. The issue with this is that it assumes that these blue numbers here that you see, which are the true utilities, are the real ones that you're seeing. Okay, but in reality, if we are suffering from implicit bias, we might not see this true utility or latent utility. So here's a very simple mathematical model of implicit bias, which is, suppose there is some parameter, beta. You can think of beta as, let's say, 0.9, or in this case, half. And for every person in a certain group, you view their utility to you, the observed utility, to yourself is half of the true utility. Of course, you don't know that. You're not doing this process, explicitly. So this is my view. So I'm, let's say, the person who can observe the entire thing. So you don't, as an individual who's making this call, you're not aware of this beta. If you were, then you would correct it, but you're not. So you just view this person as being useful to you to the extent of 5 units as opposed to 10 units. So now what would you do? What would you do? You would use the same algorithm again, but with the perturbed data set, right? So instead of the true utility of this person being 18, now it's 9. So now when you go and select the top 4, instead of selecting the top 4, which maximize your latent utility, you maximize the observed utility. And these are not the same numbers anymore. So this is a strange situation, because it's actually good for everybody if you can see the truth, because you just don't know that this person actually has higher utility for you because of your biases. Your biases are stopping you from doing this. So what can we do? One can do anti-bias training. I mean, this is the traditional solution that you can apply. It has limited efficacy. There's actually a very interesting solution to a version of this problem, which is called the Rooney Rule, which has been used in the context of the National Football League here. So the Rooney Rule roughly says that in the process of selecting who to interview for a head coach of an NFL team, you must interview at least one Black person, if I get it correctly. And there is evidence, at least in the media, that this seems to be a useful thing to do. So the question is it really, in this simple problem, does it really work? And if so, to what extent? So what we did recently is to look at the following intervention algorithm. So now we say, okay, so there's a new parameter that we introduced, L, and we say select at least L people from this disadvantaged group. So even though you don't know your implicit biases, I can still constrain you as a policymaker to say that you must select at least, let's say, 2 people from this set of women to interview. And what we can show is that, you can pick a value of L carefully, so that once I fix this as a policymaker, then you still doing what you're doing, you still doing whatever you're doing with your implicit biases, can recover the right set. So this might sound a bit counterintuitive, but there is a nice mathematical explanation for this. So we can come up with interesting algorithmic interventions in these situations. One can also ask, okay, so it seems to solve the problem locally. What about the long-term impact? So we can model this process as a dynamical system and also do experiments with people. And we can show that, under a simple and well-established rule of how humans change their opinions, which is modeled through Bayesian learning, the Rooney Rule over time significantly impacts the implicit bias. So we come up with a new way, at least, we come up with a new way as a suggestion to do this kind of training against implicit bias. Anyway, so if you're interested, you can look at some of our work on this stuff. I'm just going to end now because I think I'm out of time. So what did we see in this talk? So one of the first things is that, human decisions can appear in this objective or seemingly objective world of algorithms and make them biased. Bias can mean very different things in very different contexts, and sometimes it may be impossible to satisfy all the constraints of bias in algorithmic situations and also real world situations. And there's a great demand to design algorithms, given the rampantness of these algorithms and the impact they have already on society. There's a great movement going on, at least in certain communities, which is thinking about redesigning some of these high stakes algorithms to keep in mind the context and the stakeholders. And finally, an understanding of algorithmic bias can not only inform the design of fair or unbiased artificial algorithms, but if you view policy decisions as also algorithms acting on populations, then it also gives us insights into how to redesign policies. And some of our work is heading in that direction. You can see more of my work on this website, Controlling Bias. And Priya already mentioned, this is not an endeavor which only technical or mathematical prowess can lead you to good solutions. So here at Yale, we have a collective I like to think of. We call this Computation and Society Initiative, a bunch of like-minded people who come together to try to understand how we can address these problems from a multidisciplinary point of view. And I would stop here and thank you for your attention. And Priya, it's all over to you.
Thank you so much, Nisheeth. This was absolutely wonderful. What a clear exposition. I think, as always, every conversation with you, I learn new things. And I think what you have clearly showed us is, epistemically, algorithms serve as very effective exposers of bias, and that we can also, in turn, use them as devices to mitigate the bias in turn. So they're sort of very, very powerful and useful at the same time. So I think we have one question in the Q&A that I will read out, and then I, of course, have a couple of my own, but I will hold my horses for a little bit. So our first question is from one of our regular attendees, Jenny. Hi, Jenny. And her question is, instead of constraining the maximum bias a user can arrive at, could you also imagine other ways to push the user away from their biases? For example, showing other random contents or even the opposite of what they liked before. This could also stimulate new interests. I mean, I guess she's referring possibly to the polarization example.
Right. So I think I understand the question. Thank you, Priya, for reading it, and thank you, Jenny, for asking this question. I think in the picture, it's not the person that we are constraining. It's a representation of the person that we are constraining. And it's actually exactly doing what you're suggesting in some sense. So the constraint is on the information that we are going to show this person. So what effectively in the most simple sense, what it translates to is that, let's say we Twitter cannot show you completely polarized content. It has to show you at least, let's say 20%. Now this 20% is an arbitrary number, but let's say 20% content which may differ from your current political view. And then the question arises, how do you choose this content? Now, the real, so we all know through personal experience that if you meet a random person with a diametrically opposite political opinion, it's unlikely they will have any impact on your political opinion. So we want to pick articles which are the most likely to have an impact on you. So, I mean, in some sense, to explain it in colloquial language, I mean, if your friend or your family try to explain something to you, you might be more swayed as opposed to a person who you don't like a priori, or who you don't trust, or who you don't know a priori. Right? So the task of selecting the right articles or the right news content is a very important one. And that's really where the fine optimization goes in. So yeah, that's what we do actually.
Great, thank you. Okay, so I guess I have this other question actually, which was about the Rooney Rule. So, I'm going to stray and use my own experience as a guide, right? So isn't it true, and I think, this is echoed more generally, isn't it true that when you have one representative of a disadvantaged group amongst, in that interview example that you had, that then they come to stand for everything that that group represents, positive and negative. So that one person could much more easily serve as a trigger to our biases. But if you have two, then there's a little more noise, right? So you cannot, that's
100% correct. And that's really what our result shows. So the parameter L that I talked about is not one.
Right.
So yeah, that's right. So I think the question that was raised in the literature was, well, what can you show about this Rooney Rule? And so we cannot show much about the L equal to 1 case. But we can show, at least mathematically, we can show, that if L is something a little bit larger than 1, then it has, yeah. So I think your intuition is 100% right, that the noise kind of cancels out, right? And then you start getting the signal of the quality, because from one sample, you might get something which is pretty far off from the true, the true mean, for instance. But if you have many samples, then you get a better idea of the group.
Yeah.
So thank you for asking this question. Unfortunately, we already solved this, and this is the.
Oh,
Yeah,
great.
I can tell you more about. I can tell you more about it. I mean, I
Glad to
didn't want
hear.
to.
Glad
Yeah.
to hear that.
Yeah, but you're right on track on this one. Yes.
That L had to be greater than 1.
I mean, it means you completely understood what I said, which is which is very flattering.
Yeah. So I think there's a question from Talia. And the question is, you describe the context-specific nature of bias and fairness. What are the implications of that context dependence for efforts to develop more general AI? Are there ways to reduce bias in the application of relatively general AI tools? It's a great question. Yeah.
Yeah. So this is a very good question, but a very hard question as well. I think first of all, I mean, if I were to give a talk on AI and machine learning, I think I would first start by kind of bringing it down to the level it actually is than what the media portrays it is. So we are nowhere close to the kind of stuff that you read. I mean, there have been successes. So I'm not worried about right now general AI and but in a very specific context, let's say you design an algorithm which potentially can be used in multiple contexts, then there has to be a component there which somehow quickly recognizes or learns the context and then specializes itself to a well agreed upon notion of fairness in that context. Now, it cannot just arbitrarily choose, but I mean, so the architects of the algorithm, right, have to agree a priori, for what context, what notion of fairness or bias is important. And so that information has to be included as a part of the algorithm itself. I don't know if it answered your question, but we are very far from constructing any such thing. So, but yeah, these are the big questions, the frontiers. Hopefully, in the next few years, we will get to some of these.
Please go ahead and share and type your questions. So Nisheeth, while we are waiting for someone else, I'm gonna pipe in again. So in physics we have this intuition that when you have when the central limit theorem operates, right? So when you marginalize over many observations, you kind of get rid of the noise. I mean, would I be right in saying that isn't quite true in the kind of problems?
So that's a very precise mathematical theorem. We can, I mean, so that's, thank you for asking that question. So what does the central limit theorem say? It says the following: suppose you have random variables x1 to xn, right? And you take their average, or take the sum and divide them by square root n. Square root n is the variance, right? Let's say these are Gaussians. I mean, whatever. These are random variables with mean 0.
They are not correlated with each other.
Not correlated. Well, yeah, not correlated. But the important point is that you took n and the function that you computed of them, which is the sum, or rather the, let's say, sum divided by some number. No particular random variable has a very high quote unquote influence on this function.
Right.
So the reason why physics works is that nature has, I mean, very rarely will have functions where it is a function of many variables, right? But somehow a very small set of variables dictate the outcome of the function. So, but the kind of algorithms we are talking about in this, we are not just doing simple statistics calculation. We are optimizing. We are picking the maximum among, let's say, a set of k people or k scores or something very brittle, I would say. So there's a brittleness that comes into it. And I think this is a perfect question for our next conversation on Monday, because
Okay.
I mean, the brittleness of these algorithms is what Alexander Madhvi studies, without worrying so much about bias, but about the brittleness. And one of the ways in which you can kind of include your intuition from physics in the design of these algorithms is to smoothen these functions out.
Exactly. I was going to say,
And
use
yeah,
smoothing
so you can
filters.
smoothen these functions out. So what are ways to smoothen functions out? I mean, in mathematics, there are many ways. I mean, there are these operators. You can take a function and you want to compute its value at one point. Well, you can take a small neighborhood around you and just take the average around this point. So, you can do a short random walk or Brownian motion around this, and then take the expectation of the function. So there are various tricks in which you can smoothen the function out, and smoothing helps carry through your intuition. But what is not clear is that this smoothing will not very dramatically impact the accuracy.
Yeah.
So when you talk about, we are talking about trillion-dollar economies. Okay, we are not. This is not a joke. A second decimal place in drop in accuracy of something means many, many, many more dollars than I have
Yeah.
or I will
Huge
ever see.
consequences.
Okay,
Huge
right,
consequences.
huge consequences. So convincing a company such as Facebook or Google or whatever to move towards algorithms which are less brittle is currently an impossible task.
Right.
Because, and the only way to do that is to first formulate a regulation. I mean, um, without any regulation, which ties their hands somehow, you cannot. And for that, I mean, this is really the context of this talk. What is the purpose of this talk? The purpose of this talk is to give people, influential people who may not be experts in algorithms, but who have their influence in various domains, right? Go and have a conversation about algorithmic bias and the impact, and then eventually gain the ability at the highest levels of decision making in this country and others to have the right conversation with these tech companies, to hold and twist their arms and say, no, you have to do this. Because if you go and say, no, you do this, when this is not possible to do.
Right. Yeah. No,
Right. So
great.
I think so, but yeah, I think designing smooth algorithms is what will solve many problems, actually, not just this problem.
To be
Yeah.
continued on Monday. Thank you so much, Nisheeth.
Okay.
So first of all, there's a question from Sean Barrett. Sean is on the faculty in the physics department. Very interesting talk. Thank you. It's interesting that the Rooney Rule with L greater than 1 is seen as something that could be effective theoretically. In the sports media, recent coverage has suggested that the Rooney Rule has not been working since the numbers in 2020 are essentially the same as they were in 2003. I think they might be using L equals 1, but another issue is that the size of the pool of all NFL coaches is not that big. What L value, L equals 2 perhaps, made a difference in your own model? Thank you.
So excellent question, Sean, and a hard one. I don't know much about NFL, I must say. So I will probably not be able to address your question about NFL and why the Rooney Rule isn't working anymore. It seemed like at some point when I looked at the news articles, they seem to suggest that it has some impact, and it also was being used in other settings, corporate hiring, and so on. But I think for reasons that were mentioned by Priya. So okay, so first of all, our results hold under some assumptions, and those assumptions are that people's true utilities are distributed according to some random variables. And that has a role to play in our analysis. So if that assumption is not true, our result doesn't apply. First of all, let me just say this up front. So and so then the question, so maybe then that it suggests is that the the samples that they're choosing do not satisfy the assumptions that are required by our model, because our model does predict that it'll work. That's a possibility. And Sean, I'll be happy to have any conversation with you. So, yeah, a
So
longer
I see,
conversation.
yeah. Thanks, Nisheeth. I see Richard and Barbara, and I see them waving to say hello. Yeah, hi.
Hi,
We
Richard.
can't
Hi,
hear
Barbara.
you. Yeah, they're still muted.
There we are.
Yes.
Yeah.
There we are.
Yeah, lovely to see you both. And
Here. We enjoyed it very much.
yeah,
Thank you.
very, very interesting talk. Barbara, any questions? Do you have any questions for Nisheeth? Richard?
No, we don't. Thank you.
Okay, great. Are there any other questions, Ty? Do you see anybody else?
I don't see any others. Thank you. I think we picked them all up.
Okay, great. So thank you, Nisheeth, for this wonderful talk and for taking the time to come and speak to us today. And we look forward to the conversation on Monday to further explore these very sort of profound truths that you have helped us understand about algorithms, what they can do and what they ought to do, and what they ought to do better than they are currently doing. So I want to wish everyone a very good Thanksgiving break and a nice Thanksgiving celebration for those of you who are fortunate enough to have family celebrations and are able to travel and so on. So I just wanted to mention that our upcoming talk, the next talk in this series is going to be by Kyle Cranmer in the inference series. He's a physicist, particle physicist, and he will be talking about, he'll be addressing the issue of how do we look at very large number of events at a collider like CERN and try to infer laws, make discoveries, and so on. And before that talk, we also have, in addition, one of our distinguished book series talks and Mapping as Knowing series talk by neuroscientist Mariano Sigman. And the Mapping as Knowing series talk, this is Mapping the Brain, and that is on December 8th. So at this point, I just want to thank everyone, in particular Ty. Thank you so much, Ty, for, as always, helping make these events happen. And to Guy for helping with the AV, and to all of you for attending. And last but not least, to Nisheeth for speaking to us. Thank you very much and good evening. Yeah, bye.
Thank you
If
so
I may
much.
just mention, the post-talk conversation will be taking place at 5 o'clock on Monday, a bit of a departure from our usual time of 3. So it'll be a 5 p.m. Our regular attendees might want to take note of that. Thank you.
Thank you so much, Ty, for that announcement. Okay, bye.